Warning, the video you're about to watch contains mathematics at the level of integral calculus, also known as Calc 2. All material has an assumed prerequisite of differential calculus and a full semester course in trigonometry. A thorough review of prerequisite topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This video is for students who are in Calc 2, who are going through applications of integration and are currently in a section dedicated to applications of physics and engineering associated with integration, specifically work. So we're going to talk about the definition of work in this video. That's all it's about. Really nothing more than that. And work is the amount of energy transferred by a force acting through a distance on an object. That's all it is. And work is the product of force and distance. By the way, I should mention that prior to this video, you should have already watched videos or already be familiar with the concept of force. Now, the unit for work is known as the joule or the Newton meter. And that definition holds in the System International or the metric system. In the US, we call it the foot pound. Again, it's a foot pound because if you think about it, it's the product of force and distance. And in the US system, force is in pounds, distance is in feet. And so as creative as we are, we call that the foot pound. And as a conversion, not that you would have to do a manual conversion like this, but 1 foot pound is about 1.36 joules. Remember, joules is the unit for work in the metric system. Now, something you also need to know here is that a joule is actually an amount of energy, not a rate of transfer of energy, which is known as the watt. And we'll talk about that in a moment. But for now, very simple to compute how much work is done if you have a constant amount of force over a distance. For example, how much work is done when a hoist lifts a 200 kilogram rock to a height of 3 meters? Well, the fact that they tell us it's in kilograms and they give us the distance in meters, we know we're in the metric system. Not only that, but they've given us everything in very nice units. And since work is force acting through a distance, well, the force in the metric system requires us to include gravity, right? Because force is mass times acceleration, and then we're multiplying by distance. Kind of funny, it looks like mad, doesn't it? And mass, the mass of this rock is 200 kilograms. I kind of like to write the units underneath just to verify that I'm using the correct units in the end. Acceleration due to gravity is going to be roughly 9.8 meters per second squared. And since that's roughly, I'll actually put roughly here. And finally, the distance that we're lifting this rock is 3 meters. Now remember, the unit for work in the metric system is known as the joule, but it's actually also the Newton meter. And that's going to be helpful here because that is actually the same as saying a Newton. So this is going to be Newton and that is a meter. So this is Newton meters. So our result here will be in Newton meters or joules. In any case, this value is going to be 5,880, again, joules or Newton meters if you want to write it that way. So very, very easy computation if the force is constant through the lift. Well, because this is just a 200 kilogram rock and you're not losing any mass from this rock as it lifts, or it's not gaining any mass as you lift it, well, that is like the easiest situation. However, in your course, as you move forward, you're going to be doing stuff like including the weight of the chain that's attached to this rock to lift it up. And that weight of that chain decreases as the rock raises. So therefore, you're doing less and less work to lift that rock as time goes on. You still have, obviously, the mass of the rock itself that still gives you part of your computation, but the chain or the rope or whatever's tied to that rock, the amount of work used to lift that in addition to the rock lessens as time goes on. Now, honestly, that's all I want to do in this video, but one other thing that I'll just mention here are some interesting facts. First of all, remember the unit for work in the metric system is known as a joule. What we often hear in common everyday language is not a unit of energy, but a rate of energy. So we hear about a watt, like a 60-watt bulb or something like that. That is not like a bucket of energy. That is a rate of flow of energy. So it's a rate of energy consumed per hour. And it doesn't have to actually be per hour. It could be per second. In fact, it often is. So let's see, what is 1 watt? Well, 1 watt is the same as expending 1 joule per second. So remember, the joule is the actual amount of energy used, and a watt is the rate at which that energy is used. So a 1 watt is equivalent to 1 joule being expended per second. And that ends up being equivalent to 3.6 kilojoules per hour, or 3,600 joules per hour, which makes sense because kilo means 1,000. And that's roughly the same as the rate of energy used when lifting 1 apple 1 meter per second. Remember, it's not the total amount of energy that you use to lift that apple over a certain amount of time. It's the rate at which you're expending energy doing this. 1 kilowatt is the average rate of electricity consumed per US household. Now again, you may say, but no, I have a car, an electric car, and it may have a 17 kilowatt hour battery. And so therefore, I consume a lot more than just 1 kilowatt. Remember, this is the rate of consumption. So the average US household, not person, but household, consumes 1 kilowatt. Has a rate of consumption of 1 kilowatt. The rate 11 kilowatts is the average total rate of energy used in all forms per person in the US. And then you say, wait a second, but 1 kilowatt is the average rate of electricity consumption per US household. And that's for a household, how can the average energy used in all forms per person be 11 kilowatts? Well, it's because you're doing more than consuming electricity. You're moving, you're talking, you're driving your car, you're doing all these other things that don't require electricity. And so in all, your rate of consumption is actually 11 kilowatts. Car cruising at 65 miles per hour, well, that's roughly a rate of consumption of 30 kilowatts. Now, if that were exact, let's pretend it is, my car has, a 15 kilowatt hour, and I'll tell you what that means in a moment, battery. Well, this means that I'd be able to drive a half hour on that 15 kilowatt hour battery because I will consume 30 kilowatt hours in 1 hour. Let's see, the rate of 8 megawatts is the peak output by a big wind turbine. That's kind of nice, a rate of flow of energy. And you can read all these down here. I'm just going to end up going down to the bottom. 18 terawatts, that's the global power consumption in all forms. That's the amount of electricity flowing through all systems. And it's actually not just electricity, it's all forms. So it's the rate of flow of energy altogether on the planet. And then I'll wrap it up here with what we commonly know when you eat a Hostess Twinkie cake or something like that, a calorie, because that is a form of energy. And it can be rewritten in terms of the Newton meter or the joule. 1 kilocalorie, which by the way, on your snack foods or any type of food, honestly, when they quote calories, like 60 calories for whatever, or 100 calories for this snack bar or whatever it is, they're really quoting you kilocalories. So 1 kilocalorie is the same as 4.2 kilojoules. So you can think of those energy bars or just whatever food you're eating as a storage tank for energy. You're consuming that, it gives you energy, right? In terms of Newton meters or joules, if you prefer it that way. Now, something I had mentioned earlier, the kilowatt hours, it's not actually on this table of interesting facts, but if it bothers you that our energy unit in the United States is the watt, actually it's around the world, it's the watt, and it's not actually a bucket of energy, it's a rate of energy expenditure. The bucket is when you talk about kilowatt hours or watt hours. So that's becoming a little more familiar to people as they purchase household batteries. You might have a 10 kilowatt hour battery. Well, what does that mean? Well, that's actually, you can think of it like a gas tank in a way, and it has this unit of 10 whatevers, like 10 gallons, but it's not really gallons, it's kilowatt hours. Well, what does that really mean? Well, if your household consumption on it is 1 kilowatt, remember, if that's your average household consumption rate, that means every hour that passes, you consume 1 kilowatt hour of energy. And so that battery will be able to power whatever you're doing for 10 hours. Now, there are a lot of things that an energy expert will tell me are completely wrong about what I just said. One being that no system is perfect. You will have an amount of loss just due to resistance on wiring and circuitry. And so therefore, that 10 kilowatt hour battery will not actually deliver 10 full kilowatt hours. It delivers less than that. Also, if your rate spikes for an hour, that will use actually more than 6 kilowatt hours because of just the fact that you have to open a larger pipe, basically, for all that energy to flow through. There's actual loss due to that as well. In the long run, we really have two basic units of energy, the joule or the kilowatt hour. And the kilowatt hour, sometimes we would divide that by 1,000 and call it the watt hour. Just depends on the size of the units that we're associating with whatever we're talking about. So that is an amount of energy either available or used. And the watt or the kilowatt, well, that's a rate of energy consumption. And I find it better to say it's a rate of energy transfer because technically you're gifting that energy to a different object or a different system. So it's not lossless. You actually do give that energy to something else, and that something else uses that energy. It might give that energy back to something else or whatever. So it's not actually consumed and never had again. Anyhow, the main thing about this video is just to understand that work is the product of force and distance. Force enacted on an object through a distance. All right. I know I'm not an expert on energy and rates of energy and rate of energy consumption or transfer. So please forgive me if some of the stuff I say here is slightly ignorant, but it's close enough. So, all right. I hope this helps you in some certain way, and I hope to see you in future videos. You have a great day.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Says, listen close. Don't talk too much that isn't cold. Sure, you may really hurt inside. It doesn't justify you to speak too loud and cry. Don't whine. Just